This is Mrs. O'Neill for AP Chemistry, Chapter 17, Section 2, Buffered Solutions. You should have watched that intro lesson on pH and buffers, and here are my notes. I'm going to go through them kind of quickly because I want to make sure I have enough time to get through everything else. He talked about proteins in our blood and how they have a specific pH range. And if they don't have this range, they can't do their job and they start to denature. So we can use this as a buffering system. So here's our equilibrium. He talked about how in a buffer solution, if you add protons or H+ ions from a strong acid, it's going to simply shift the reaction to the left, according to Le Chatelier's principle. And then if you add more hydroxide ions from a strong base like OH-, it will push the reaction towards the right. So either way, though, we're going to fairly keep that pH stable. Gave us a nice flow chart, and I want to bring your attention to this ratio. It is not the K equation. The K equation, the equilibrium equation, gives us products over reactants. This is a ratio between the weak acid and its conjugate base. So keep that in mind as we move forward. So here's our weak acid in equilibrium. We have our HA weak acid forming our H+ ions and our conjugate base. So in a good buffer solution, we want to keep that weak acid and that conjugate base as equal as possible. So he said, well, we're going to add a strong acid, H+ ions, and according to Le Chatelier's principle, that H+ ions are going to react with the conjugate base and push the equilibrium to the weak base. And if it does that, the pH might go up, but very, very slightly, so it is very stable. So again, according to Le Chatelier's principle, I'm adding more H+, which is already on the right side. I'm going to shift it to the left, making more weak acid. And then the other way around, if we have our equilibrium again, we have our equal volumes of, or I should say our equal concentrations of our weak acid and our conjugate base. We're going to add our strong base. It's going to react with the weak acid this time because it's going to be a neutralization reaction, and it's going to shift it to the right according to Le Chatelier's principle. So we increase a little bit of our conjugate base, but again, not so much to interfere with that pH level. So then he went on to talking about that equilibrium constant, and remember that K equation is products over reactants. But in everything in this equation, what we are interested in is that H+, because that H+ concentration gives us that pH value. So remember that pH equals the negative log of H+, and so how can we keep that good buffer solution as stable as possible? Well, again, we want to keep the concentrations of the H+ and the conjugate base A- equal as equal to each other as possible. We want this ratio to be as close to 1 as possible. And he wanted to also tell you that that pH is our H+ concentration. They're related to each other, as well as the pH is also related to the pKa. So again, if we keep that ratio as close to 1 as possible, we can actually change each of these tenfold, increase them as much as tenfold, as long as each of them increases and we keep that ratio equal to 1, our pH level actually is only going to change 1-fold. So that's how we keep that good buffer solution pH stable as possible. So again, we want that equal as much as possible. So that pH gives us also the pKa, and he talked about how if the pH is less than the pKa, you really have more acid, and if the pH is more than the pKa, you have more base. So he kind of said on a seesaw, if the pH goes down, you're going to have more acid, and if the pH goes up, you're going to have more base. So this might be a nice visual for you. He also talked about indicators, and an indicator is just going to tell us, is the solution neutral, is it less than neutral as an acid, or is it more than neutral as a base? So again, there's different indicators for different pH changes, and there's more on that later. So he went back again to the proteins and the amino acids and how that buffers help biologically. You also should have watched the preview video that I put on there, and here's a little bit of a recap. Here's our conjugate acid-base pair. Again, that's what we're really interested in. We're really interested in our HA and our A-. We're interested in the relationship between the two and how the ratio of their concentrations are. So again, if we're adding more H+ to the system, according to Le Chatelier's principle, it's going to react with the base, forming more of that weak acid, resisting pH change. And if we add more strong base or more OH- ions, it's going to cause a neutralization reaction because we're going to react it now with the acid, again shifting it to the right side, making more conjugate base and water. I do want to bring that to your attention. In this particular reaction, you have to remember to add that water to make sure that it balances correctly. So back to your notes packet, the objective for this section is to consider the composition of a buffered solution and learn how they resist pH change when small amounts of a strong acid or a strong base is added. That's another key word there, small amounts. Of course, if we continue to add a lot of strong acid, it's going to change that pH value. If we continue to add strong base, it's going to change that pH value. But in a buffer solution, we can actually add small amounts of that, and the pH is going to be stable. So pause the video, fill in the words, and then play to hear my words. So a buffer is basically a solution that resists change in pH. So there are two ways to make a buffer, a weak acid and its salt, which would be an ionic compound. And in that ionic compound, one of the ions is going to be the same as this weak acid. Same thing with a weak base and its salt. One of the ions in the salt is going to be the same as in that weak base, kind of like that common ion that we already discussed. So we can make this buffer any pH that we want by varying those concentrations, but then adding that little bit of strong acid or strong base kind of keeps that pH stable. So how do we know, or how can we make a buffered solution? Again, both species are going to neutralize that OH ion, and a basic solution, we're going to neutralize the H+ ion. So again, that's just similar to the reactions you've already seen. So how do we make a buffer solution? Well, we need a weak acid base conjugate pair. In other words, we need a weak acid and we need one of those ions from a salt. So here's an example down here. We have that weak acid, and here's our conjugate base that we want. So we would need to add a salt of either that acid or base. And in this case, if this is the acid, we would need to add something like NaC2H3O2 to that weak acid to have that common ion. Same thing down here. We have the ammonium polyatomic ion to add to ammonia, which would be the weak acid. So maybe something like ammonium chloride, since the ammonia would be the same, or the ammonium polyatomic ion, I should say, is similar. That is going to be the common ion. That would be a good buffer. So if we look at something like this, what could you possibly add to a weak base, a weak acid of HNO2? Well, think about this. You need some kind of salt or some kind of ionic compound that has that NO2 polyatomic ion in it, and that would be that common ion. So something like sodium nitrite or potassium nitrite or lithium nitrite. Then you would have a nice buffer solution. So pause the video and see if you can come up with the answer. Hopefully that makes sense, and you're probably thinking, it is the same ion, but remember, HNO3, nitric acid is strong, therefore NO3 is actually a spectator ion, and we want to remember that buffer needs weak acid conjugate base or a weak base conjugate acid, okay? So you always need something weak in there. So how does this buffer work? Again, it's going to be the relationship between that weak acid and that common ion, aka conjugate base. So you can have acid over base, or think of it as the weak acid over the common ion. So we want to remember this equation, and this is what he showed us in that video. So there are two factors that will determine the pH, the value of that Ka from that weak acid component, and again, that ratio of that conjugate acid-base pair. So we already talked about this. If we're adding that hydroxide ion from a strong base, it's going to react with the acid, causing a neutralization reaction, forming that water. And that's why I keep saying neutralization reaction, because it forms that water plus more of that weak base. So if you read that information, that's basically what I said, but think of the HX and X minus, really that ratio between the two doesn't change much. So it's going to resist a change in pH. If we add H plus to our buffer solution, it's going to react with our base, forming more weak acid. And again, the ratio between the conjugate base and the weak acid, that ratio is going to be so small, that ratio change is going to be small, that the pH doesn't change either. So this is exactly what he showed us. It's another nice visual. This gives you a true reaction, not just HA, but HF, and its conjugate base of F minus. So again, if we're adding more hydroxides, the hydroxide is going to react with that base, causing a neutralization reaction, forming more conjugate base and water. And if we go back to the original buffered solution and add more H plus, we're going to react that H plus with the conjugate base, forming more HF. But either way, that pH level is not increasing or changing very much, increasing or decreasing. So again, pause the video and see if you can come up with some answers. And hopefully that makes sense. So how do we calculate the pH of a buffer solution? Again, it's this ratio of the weak acid and strong base. So this is called the HH equation. It is very similar to what you saw, except it's twisted, okay? It's backwards. So the pH, our pH value is going to equal our pKa, but we're going to add the log of the opposite of what we just talked about. So it's the base over the acid. And guess what? It's on your reference sheet. So it's nothing that you have to memorize which order it goes. And we also want to remember the pKa equals the negative log of Ka. So when we were asked to form or asked to calculate the pH of something, we want to remember that if they give us a Ka value, to take the negative log of it before we plug and chug into our equation here. Okay, so that's the equation we're going to use. And buffer capacity just basically says how great or how strong or how much that buffer can resist that pH change. That's all the buffer capacity is. So again, depending on the buffer and depending on that solution is going to tell us how much that range, how far that pH range can go before it gets pushed over the edge. So if we look at this problem, what is the pH of a buffer? We're giving you the concentration of a weak acid, and we're giving you the concentration of that salt, and we're also giving you that Ka value. So we used to do all this, right? We used to do this whole gigantic ice box. We talked about the common ion, we plugged and chugged, and we would get the pH value of 3.77. Well, now, shortcut, we can do this. Now, as long as you know your values and what they represent, now we can plug and chug and use this HH equation. So again, our Ka here, but we're going to take the negative log in order to get the pKa. We have our concentration of our base over the concentration of our weak acid, and we get 3.77. So it's exactly the same way, or exactly the same value as using the ice box. So you can do it either way, but this is a nice shortcut when we're talking about a buffer. So give it a try, use the HH equation, pause, and then play and make sure you get the right answer. So hopefully nice and easy for you. Just make sure that you're doing that log of that ratio correctly in your calculator. So again, if we give you an addition to a strong acids and strong base to the buffers, what happens? We don't really have to do these kinds of problems. on your AP exam. So I'm just going to show you what happens as a visual. So again, what happens, here's our pH. If we add more OH, again, the pH is going to slightly go up. And if we add more H+, the pH slightly goes down. We used to have to do these kinds of problems where you have to figure out exactly what that pH value is, but no longer. But just know, again, that buffers resist change in pH. Okay, see you in class.